All right, welcome to the Explainer. Today, we are going to tackle a tiny little component that, no joke, powers our entire world. But, for a lot of people, trying to understand it starts with some seriously tough-looking questions.
I mean, if you're a physics or an engineering student, you've probably had a cold sweat seeing something like this, right? These kinds of questions pop up on exam papers all the time.
And let's be honest, at first glance, they just seem so abstract, so complex, maybe even a little intimidating.
Yeah, you start seeing terms like depletion region and biasing, and it's enough to make your head spin. But what if I told you the core idea behind all of this was actually incredibly simple? Seriously, let's just dive in. Forget all those complex terms for a minute. Just picture this, a simple electronic gate. Or even better, a one-way street for electricity. That's it. That is the whole big idea, right there. So this one-way street has a name, of course. It's called a diode, and it's what we call an active component, which means it plays a really special hands-on role inside a circuit.
See, its whole job is to control the flow of current. It'll let electricity pass in one direction, no problem, but it completely slams the door shut if that current tries to come back the other way. Kind of like a one-way valve, or even a turnstile at a stadium. And this is a really key distinction. You've got your passive components, like resistors, that just kind of sit there and consume or store energy. But active components, like our diode, they're the traffic cops of the circuit. They are actively directing the flow. So the big question is, how in the world do you build this amazing little one-way street?
Well, it all starts with a very special class of materials. I'm talking about the absolute foundation of, all modern electronics. Semiconductors, these materials are so cool because they're unique. They're not great conductors, but they're not great insulators either. They're right there in the middle. And that in-between property means we can precisely control how well they conduct electricity just by adding tiny specific impurities. It's a process called doping. So here's how it works. You take a piece of pure silicon, and on one half, you dope it with impurities that create what we call a p-type side. This side has an excess of positive holes. You can just think of them as little empty parking spots waiting for an electron. Then, on the other half, you add different impurities to create an n-type side, which is loaded with extra, free-moving negative electrons. Now, the real magic, that happens right at the border where these two different regions meet.
Okay, so right at that junction, what happens? A few of those extra electrons from the n side just naturally jump over to fill the empty holes on the p side. And when they do that, they create this thin, electrically neutral barrier. We call it the depletion region. And this region acts just like a closed gate, stopping any more electricity from flowing across. It's a natural roadblock.
So, okay, we've got this gate that's naturally closed. The big question is, how do we open it? And for that matter, how do we make sure it stays closed when we want it to? Well, we use an external voltage. It's a process called biasing.
And this is where it all comes together. If you connect a battery with the positive end to the p side and the negative end to the n side, that's what we call forward bias. This pushes the electrons and holes toward each other, that barrier shrinks, and boom, the gate opens and current flows right through. But what happens if you flip the battery around? Now, that's reverse bias. This pulls all the charges away from the junction, making that barrier even wider. It basically slams the gate shut and locks it.
So this totally predictable one-way behavior, it creates a unique electrical signature, a kind of fingerprint for the diode. And guess what? This brings us right back to those scary-looking exam questions from the beginning.
So how can we actually see this on-off state? How can we map it out? We use something called a VI characteristic curve. And really, it's just a graph of the diode's personality. And here it is. This graph just brilliantly shows everything the diode does. The horizontal line, the x-axis, that's the voltage we're applying. And the vertical line, the y-axis, that's the current that actually flows because of that voltage. Let's really look at this thing. Over on the right side, that's forward bias. See how as you increase the positive voltage, almost nothing happens? It's flat, until you hit a specific point, right around 0.7 volts for silicon. We call that the knee voltage. And once you cross that tiny threshold, the gate is wide open, and the current just skyrockets. Now look at the left side, that's reverse bias. It's basically a flat line. Almost zero current gets through, just a tiny, tiny little leakage. That is until you apply way too much negative voltage and hit the breakdown point.
At that point, the gate is basically blown open and current rushes through uncontrollably, which is usually not a good thing.
Okay, so let's zoom out for a second. Let's look at the bigger picture here and see how this simple little gate, this one-way street, led to one of the most important inventions in all of human history. No exaggeration.
Because this simple PN junction, it's not just another component you solder onto a board. No, it's a fundamental concept. It's an idea, and it's the parent of an even more powerful, truly world-changing invention. I'm talking about the transistor. You can basically think of a transistor as two of these diodes built back to back. What this does is create a special kind of gate, one where a tiny little electrical signal can open or close the gate for a much, much larger flow of current. In other words, it lets a small signal control a big signal. It acts as a perfect electronic switch. And that ability, the ability to switch, to be either on or off, well, that is the foundation of all binary logic. It is the ones and the zeros that run our computers, our phones, literally everything in our digital lives.
So, here's the final thought I want to leave you with. Every single time you use your computer or your phone, or, well, anything with a chip in it, you are commanding billions, literally billions of these fundamental PN junctions. They are all working together as tiny, perfect switches, opening and closing millions of times a second just for you. And it all starts with that simple, elegant concept we talked about at the very beginning, a one-way street for electricity.